So I would also like to welcome everyone to our third research meeting and many more to come. So the format will be very similar to previously. So before we get started though, I'd like to introduce John Webb, our sponsor, and give him a chance to talk.
Thank you, Dave. And I'd like to start off by saying that Dave Rice, of course, is one of our founding members of the Ivan Group. And I would like to dedicate today's meeting to the memory of Dave's wife, who has left us just a couple of days ago. And we all have fond memories of Karen and Dave. Our sympathies from all of us to you.
Thank you, John. Yeah, that's nice.
You're welcome. And
yeah.
Once again, welcome everyone. We're very happy to have everyone attending our Ivan meetings. They've obviously become quite popular, and our resources is very happy to sponsor. We've been around for 35 years, of course, providing reconditioned Brooker and variant NMR spectrometers, services and parts and so forth. And also our co-sponsor, Q1 Instruments, Don Bouchard. Maybe you could say a couple of words, if you would, please.
Okay, thank you, John. We invite you to get to know Q1. Q1 designs and manufactures complete NMR spectrometers from 400 to 600 megahertz with features for routine use and the research laboratory. Want to upgrade an older system? Q1 can retrofit AS and UltraShield magnets with complete upgrades, including automation, for less than you think. Q1 offers NMR instruments with excellent performance at an unbeatable price. Experts know the probe is the key to performance, and Q1 offers smart tune and match probes made by Q1 Tech. Our probes have a robust hybrid tuning mechanism, which means faster tuning, unmatched reliability, and improved throughput. Our STM probes are a patented design with hybrid tuning that is free from drift and hysteresis for consistent performance, excellent signal and noise, superior solvent suppression, and are made by the renowned Q1 Tech team in Zurich. Q1 Tech is innovated to produce the world's first multi-platform probe, fully integrated into Topspin and VNMRJ platforms. The Q-Link Ethernet-based interface can be installed on a wide range of consoles to fully automate the operation of older NMR systems and add multi-nuclear capability to a dual-channel system. Q1 Tech also offers custom STM probes up to 600 megahertz, such as this 3-channel high gamma probe for pharma studies, optimized for tritium observation and providing a wide range of decoupling and correlation experiments. Want to know more about our probes, consoles, and complete systems? Contact us for a no-risk remote demonstration. Thank you.
Thank you, Don. Good information and good product lineup. I'll now ask another one of our founding members, Dan Iverson, if you would, to say a few words about upcoming meetings and also Ivan Spin Sites, which you've been doing a wonderful job taking care of these days.
Krish, another one of our founding members, is the organizer of these technical sessions, and unfortunately he can't be with us today. So I wanted to just mention the next meeting he has organized is on covariance processing with David Schneider from the William Patterson University. And the schedule is not quite set yet, but most likely it'll be the week before Thanksgiving. So that will put that on your calendars, and there will be an announcement coming up. And I also, as John mentioned, the Ivan Spin site is now live, and I will send a chat message around, which I just did, with the link that you can, if you'd like to join that meeting or that forum.
Thank you, Dan. And with that, I'll turn things back over to David. And David, if you'd like to get things started off for us, please.
Okay, right. Our panel leader is Thomas Williamson from the UNC Wilmington. And I'll just mention briefly the format. His panelists will be talking for roughly the first half an hour. And during that time, you should certainly send your questions to the chat, and the panelists will be monitoring the chat. After the talks are done, then we'll open up the floor to everyone and to ask direct questions, and we can keep discussing as long as there's interest. With that, I'll turn things over to Thomas.
All right. Well, thanks, Dave, and thanks to all of you for coming today. And this is obviously a topic that, for those of you who know me, a topic that I'm very passionate about and have been involved in for at least a couple of decades now, to show my age. But whenever I was asked to arrange a panel to talk about this topic, I thought about, who better to talk about the one bond and heteronuclear, or one bond and long range heteronuclear coupling constants than Alexie Buevich from Merck and Teodor Parella from University of Barcelona, who I've been working with for a long time on this subject, and then of course Roberto Gill with some applications. So just to kind of kick things off, I think that these one bond and long range heteronuclear coupling constants, although they're being applied more and more each year, there's still somewhat of a overlooked NMR parameter with a tremendous amount of informational capability. And so if we consider the sort of standard NMR parameters, our 1D proton NMR chemical shift, our 1D C13 NMR chemical shift, and then of course all of our sort of routine toolbox of 2D correlation experiments, our COSY, HSQC, HMBC, so on and so forth. These experiments are very good for helping us, put together the constitution or planar structure of a molecule. Traditionally, we've then turned to our 3-bond proton-proton homonuclear coupling constants and their Karplus relationship, or whatever flavor of these angular dependence on these values that you like to use. And then, of course, our NOE or ROE experiments to look at our through space interactions within a particular molecule. Of course, if you joined us last time, or not last time, but in the Ivan meeting before last, and you heard us talking about the application of anisotropic NMR parameters. And then today we'd like to extend this set of parameters even further with the 1-bond proton-carbon coupling constants and long-range proton-carbon coupling constants. So the first thing that one needs to be able to do when they want to utilize these values is to actually measure them. And of course, certainly the measurement of these has become easier over time. And hopefully by the end of today's presentation, you'll be convinced that the utilization of either one of these parameter sets is much more powerful when used with density functional theory calculations. So in order to measure our basic 1-bond proton-carbon coupling constants, I'm sure many of you, like myself, were always taught in the old days that, your standard HSQC experiment is really great because it refocuses all of your proton-proton homonuclear couplings, your chemical shift, and your proton-carbon heteronuclear couplings throughout this sequence. And it turns out that that's only partially true. In fact, you actually have a number of other terms that are present in the evolution of this magnetization. And it turns out that we can actually purge most of this unwanted anaphase magnetization by using a few tricks which we've discovered over time. One is a so-called perfect echo, which is a sort of older pulse sequence element, but works beautifully here to cancel out some of this unwanted terms in this magnetization. And then also the widely applied clip or a heteronuclear decoupling to remove these other terms. And as you can see here, the perfect echo is basically just adding another echo for on your proton channel and on both sides of your chemical shift evolution. And basically the idea is that it refocuses any mismatch in your pulse sequence. And so if you have misset parameters for the proton-carbon coupling constants, or have some sort of unusual homonuclear couplings, as you can see here, that between the perfect echo in the clip pulse sequence modules, we can really nicely refocus these and give us a beautiful baseline free of any antiphase contributions which could hinder the measurement of these coupling constants. Over time, we also found that you could take, you could approach this a different way by using a zero quantum filter. And this was introduced into our original pure in-phase HSQ and BC type experiment. Basically, you're just applying a adiabatic pulse in the presence of a pulse field gradient, which allows us to destroy any of this unwanted zero quantum magnetization. And this can work for one bond HSQC type experiments or long range HSQ and BC experiments. And once again, as you can see here, it allows us to really nearly perfectly refocus everything or destroy any of these terms that we don't want, and gives us a really nice baseline free of any interactions that we don't want to observe, and allows us to really accurately measure these values. So as time went on, of course, things continued to evolve, and at this point, we take Teo and Roberto's sort of combination of all of these ideas, where you basically take the perfect bird and the zero quantum filter. You can apply multiplicity editing if you want, and basically we present these data in a pure shift format, so you can actually use bird-based decoupling during bird-based homodecoupling during your acquisition, and so basically convert simplify the multiplicity of all of your homonuclear multiplets or all of your proton multiplets, and then we just display these in a 2D J-resolved manner. And so this works beautifully and allows us to really accurately measure these valuable parameters. One of the things that's sort of I guess taken away from the value of these parameters over time is they're surprisingly difficult to calculate. We can calculate long-range heteronuclear coupling constants with no problem. We can calculate 3-bond proton-proton homonuclear coupling constants with no problem. Of course, we can calculate chemical shifts, but the one-bond proton-carbon coupling constants have been sort of a nagging problem in that they tended to be overestimated by around 5% or more. And although this doesn't seem like a lot, the range of coupling constants that we're typically utilizing here sort of make that 5% very important and sort of limited their application. So one of the things that Alexie's actually been working on and did a marvelous job with is actually trying to understand exactly why these calculated coupling constants were overestimated, and see if we couldn't figure out something to do about it. So at this point, I'll turn it over to Alexie and let him fill you in on that aspect of this work.
Okay, so as Thomas alluded to, so we can calculate using the DFT basically any NMR parameter right now, and some of those calculations are pretty accurate, and we have been using that for more than 20 years already, and sort of get an experience what kind of errors we can get. And it was somewhat unexpected for us to find that usually used and so loved B3-lib method, which is we use in functional for calculating of the heteronuclear homonuclear couplings, specifically for one-bond GCH coupling, was given quite a big systematic errors, as Thomas showed on a graph in the previous slide. So it was systematically shifted by about 5 to 10 hertz. And so that brings us so our attention to sort of revisit what's the problem with that. And as it turns out that it has been for a while a topic for quite extensive studies. And here is just a short list of the groups which have been involved in calculating specifically one-bond GCH couplings. And as you can see, the number is just the tip of the iceberg, I have to say. This is just a very short list of these papers, but the groups from different places have been really working hard to sort of understand and understand what's wrong with these calculations. Of course, we're talking about DFT calculations. That is our main tool right now, because the high accuracy calculations as ab initio basically it cannot be used for large molecule more than 200 molecular weight. That will be too slow and not amenable for this kind of problems. So the DFT has been studied then extensively to find the way to compensate. And generally speaking, all of this work would be required to push the accuracy to the limit. And the limit was estimated as RMSD below 5 Hertz and the maximum deviation of the coupling less than 10 Hertz, which is for reading these papers, you can say this is not a very good accuracy anyway. But even that was a struggle. So in order to accommodate these errors, many researchers have been using additional scaling, additional empirical parameters to bring the data together. And that worked for some extent. So in addition to that, so what has been done is the differentiation of different types of carbons based on the hybridization and using then the scaling factors for each and every carbon type of carbons. So it's an addition. So as a top of that analysis, I would mention the work by Andrei Kutredeladze and group, which is using 28 parameters just to improve the calculation of JCH couplings of different type. I have to say, not only one bond, but multiple bond as well. So the empiricist which comes with this analysis actually gave us some thought, where does that come from? And so we screened a multiple sets of DFT functionals and basis sets. And what we found that all of them are really not very good performer. And it turns out that the basis sets that is circled here in red, that's the preferred theory to analyze any coupling. So if you want to analyze coupling, we would start with that one. As you can see, the RMSD is higher than 5. I also have to mention that there is something which somewhat has been overlooked by other researchers, or maybe not overlooked, but somewhat missed and in a basic research. That is the application of so-called NMR mixed settings. That has been done in the Gaussian program that we love, and that is NMR mixed settings for calculations of the J couplings. It specifically was used for optimal analysis of the J couplings for DFT. And in 2006, the work by Deng, Cheeseman, and Frisch implemented that in Gaussian, and we currently using that all the time. Those groups which are not using Gaussian, they have to come up with the other solutions, and for that reason, the optimization of the basis sets has been done. Those are which is a -Z, there's J here. Let me show. This is the basis sets with the -G. Is actually doing the same work as NMR equal mix in a Gaussian. But in a Gaussian, this is kind of standard. This is just a change by keyword. Here, if you start using that kind of a setting, you will pay for that by the very long calculations, and I will show in the next slide how that was. So we thought that using that mix maybe will help us to find the best solution, and indeed. So the green basis set that we found here with the B3LEAP was given the error about 3.2 Hertz, which was already better than our standard way of calculating. The same errors we are getting with that analysis with B3LEAP TZVP with spin, and that has been found at least by two groups, by Sam Fabian and by Ho mentioned in the previous slide. So as being one of the best. As you can see, so we sort of matching with the mix analysis here, the accuracy, but by no standards 3.2 is the best. So what we also, so here is my point that using the newly found optimized DFT analysis is very economical. And if you compare the one which has been previously published as this one, at least twice as faster, given the same accuracy, which is very important if you're thinking about the analysis of the logic coupling of the molecule. In this particular case, that was in strychnine. Yeah, by the way, that's everything has been done for strychnine. It's about 1,000 different coupling constants have been calculated here on a Linux cluster. And this table also is kind of very clearly shows how slow could be calculations if you're using these -J or J-optimized basis sets that has been developed mostly by the Sauer group. And you have to wait basically 15 to 30 days to get the results, whereas here the calculations within 3 hours you can get the result. As I mentioned, 3.2 difference that we were getting again was very systematic. So it was something which is underlying the systematic error of the DFT, which brings each and every parameter coupling constant slightly larger. And there's a known fault of DFT that is the distance, the geometry is not as perfect as one would wish that would be. And so what we have done, we just tested how is this RMSD dependent on the CH bond distance. And it turns out that it's even a small change of 0.05 of the angstrom. If you change it systematically for each and every bond, can bring down the RMSD from 3.2, as we found here, to about 2. And that would be like almost a record value. No one, even with the scaling factors that are out there, will be getting is better than that. On the plot on the right is also shown how the J couplings are scaled. You see that all of them go in almost linear based on the distance. So at that point, we are thinking, okay, probably the better geometry would be the solution for this problem. And indeed, so we scan a little bit of different, different basis sets and the functionals for the DFT, including MP2 methods. As the higher the accuracy of the basis set we would apply, the lower the RMSD here. And there is a general trend when we calculated the distance between the two atoms, and it was following the similar trend. In this case, particularly, the change of 0.05 of the angstrom would bring the RMSD from 3.2 to 1.7. We could include also the PCM solvent effects of the model, intrinsic model in the DFT calculations, and you can even go down to 1.6 hertz, really the number which is close to the record that we can get by any other means. What I hear is well, that has been done on strychnine. Is it working for each and every compound that we have said? In order to cross-validate the data, so that set of parameters we have applied for the big set of 119 J couplings collected and analyzed by Kotiladze and Mukina in their work when they were coming up with their way of calculating. And it turns out that this the fitting was pretty good. RMSD was 2.7, which is considering the accuracy of the measurements of the coupling as well, I have to say, and the difference of the solvents. That RMSD, I'm not surprised that this is a little bit higher, but still it's pretty good. The only parameters that we couldn't fit with that, our preferred now way of calculating is alkynes, and those were off. And for those we found multiple methods which can improve the alkyne calculations. Here they are listed here if you're interested. So basically using for each and every molecule with the sp3 and sp2 carbon hybridization, that's the way to go by our standards, and for alkynes is this one. I have to say, at this point, we are not using any post-processing or scaling. This is a pure DFT calculations, and which is a sort of our goal was at the beginning. We don't want to put any additional scaling into the analysis of the couplings, and I think we reached that goal. So having this very high accuracy data, what we are reaching, what kind of other problems we can pose, and here is the first example that we tested. It's our favorite molecule, strychnine. So as you know, the strychnine could have 3 different conformations, and it can have 13 possible isomers Of course, it's 64 altogether, but none of them will be physically possible. So only 13, and we have published in 2013 the same set of data analysis for the one bond CC couplings. Here is we're using the same set of diastereomers and 3 conformations to check the J coupling analysis, whether we can differentiate the natural strychnine from all this set of conformations. So, and here is the plot where it clearly shows that RMSD, shown is in the blue bars, and the maximum deviation in the red one is the lowest for 1A isomer of the strychnine. This is a natural one. Each and every one was higher, and that means that we can use the one bond coupling to actually differentiate different isomers of the molecule, which is pretty impressive, I would say, considering the, and impressive because it became possible only when we have that high accuracy. If the accuracy would be worse than that, I'm assuming that it will be more difficult to determine these isomers and as well as the conformation. Well, that we didn't stop on that. We also cross-validated some other structural problem, which is the real world problem. This is a trichalabane deuterapen. The structure analysis has been sort of difficult. We tried the CC couplings, it didn't work. With the homonuclear experiments with the ROSI, we were able to determine the stereochemistry. And that's why we know what is the correct isomer is. It's isomer number 14, molecule 14. The other problem with this molecule was that it has a partial flexibility here. So all these groups are rotatable. So you have to sort of come up with the ensemble of the conformations. So in addition to that, so 6 different isomers we were testing, calculating the J couplings for the ensembles, then averaging them using the Boltzmann distribution. And 23 couplings have been measured, and then we compare the theoretical ones with experimental. And what we found that 14 again has the lowest RMSD, the lowest maximum deviation, and the highest correlation coefficient. So altogether, I think with this improved DFT analysis that we are showing, and the not only us, I have to say that if you can also go in parallel analysis that has been developed by other group with the best approaches there. So we probably will be in the same level of the accuracy. But what's probably the biggest conclusion from this work is that the one bond coupling becomes as instrumental as a multiple bond coupling, which is known to be very structure sensitive because of the dihedral angles analysis. Here there is no dihedral angles. This is only one bond and orientation in the space, and that is a quite important factor to put in together and improve overall the analysis of the structural analysis of the organic molecules that we are looking currently. On that, this is my last slide. I just want to acknowledge the work that the collaborators which have been part of that work, Theo, who is here, Joseph, my colleague at Merck, people from Italy, Giuseppe Bifulca and Nunzita Tomasi, as well as the Thomas and Gary Martin, who have been at Merck at that time. We have been doing that work. And I'm passing the ball to Theo, who is going to talk about how to measure these couplings, because the experimental part is and still is an important factor for our calculations. In order to get the coupling very accurately, you need to use the modern experiments, because none of those the old ones approaches would be working in this particular case. Thank you.
Okay, thank you, Alexei. I will talk about the experimental part, how to measure long-range proton-carbon coupling constants. This is a topic of interest for chemists for many, many years, 3 or 4 decades ago. There are many, many methods published, and we don't have a general method accepted for everyone to measure these coupling constants. All the methods have pros and cons, and then I would like to present some tips and tricks about the measurement of these coupling constants using as a guideline a tutorial we have published this year in magnetic resonance in chemistry about one experiment. This is an HSQ-MBC experiment based on proton selection. And then from this basic experiment, I will present some modifications and then this is the reference of this tutorial. Then the question is, there is a question for us is why the chemists in general don't use the proton-carbon coupling constants as a tool for structure elucidation when the typical proton-proton coupling constants or NOEs are not enough. And then the major challenge is the natural abundance of carbon-13 is only 1%, and that means when we analyze the proton spectrum, we only see in principle the large proton carbon-12 magnetization, the signal arising from this magnetization. When we analyze the spectrum in detail, we can see the satellites that corresponding to the one-bond correlation. That is important that to demonstrate the power of the NMR spectroscopy to analyze mixtures of magnetically different molecules is, for instance, the measurement of the proton carbon coupling constants measurement. Usually, the satellites correspond to the 1% of the isotopomer where the carbon-13 is directly attached to the proton of the observed proton, like this. Then, in addition to this, in this case, this is menthol. Menthol has 10 carbons. That means that exists 10 different isotopomers with one single carbon-13 in their structures. That means that below to the large signal that we observe in the proton spectrum, in the case of menthol, we have other 9 signals from each one of the isotopomers of menthol. And then usually the satellites, the one-bond correlations are extracted from HSQ-MBC experiments, and usually the long range are obtained from HSQ-MBC or HSQ-tox experiment. Then this is the power. The first challenge is to measure this signal that are below to the intense proton carbon-12 signal, and also the other challenge is to detect and to observe this signal in optimum conditions. Then these are the basic experiments to measure proton carbon coupling constants. HSQ-MBC for one bond. For 2 and 3 bond, HSQ-tox, HSQ-MBC or HMBC. The problem of HSQ-tox or variants of these experiments, for instance, at log or EK8, there are many versions of the HSQ-tox. The problem is this experiment only works for protonated carbons. But the experiment works very well because provides information about the sign and also allows the measurement of very small coupling constant values. Then the question is, cannot be considered a general method because if you have non-protonated centers, these centers will not be visible with this method. Then, if you want to obtain information about ultra long range correlations, is 4, 5, 6 bond correlations away, is needed modifications of the HSQ-MBC or HMBC experiment. One possibility is the long-range HSQ-MBC or an hybrid experiment and HSQ-MBC-COSY, HSQ-MBC-tox experiment, and also in molecules having a low density in protons, having many contiguous non-protonated carbons, it should be useful. It should be useful to use carbon-carbon coupling constant using adequate experiments. Then, just before to select one experiment, we need to have clear some questions, because the first question is if you want to obtain information, qualitative information or quantitative determination of these long-range correlations. Long-range correlations in principle means 2 and 3 bond correlations, but it's possible to obtain information and measurements in 4, 5, 6 bonds away connectivities. Another important aspect is the accuracy of the measurement, because long-range proton-carbon coupling constants in general have the same size as proton-proton coupling constants, is as between 0 and 10, 12 Hertz is the normal magnitudes we can find. And then the problem, as any experimental measurement, we have an error in the measurement, and then it's very important that to reduce at maximum the error we can introduce in the measurement. This is important, very important, when you want to measure very small coupling constants. Another aspect to discuss is the simplicity of the measurement. Then the more easy approach is the direct extraction, in the same way that we extract proton-proton coupling constants from the proton spectra. But in many cases, this is not possible. And then exist many methods using fitting, G-resolved representation, spin state selection experiments using ECOSY patterns, IPAP patterns. But it's very important, if we want that these parameters to be used for the non-expert users, is very important to have a methodology that the extraction of the magnitude of the coupling constants is easy. This is a good condition. If not, the problem is then these parameters are only used for the experts. Another important question is the fast determination and the potential automation of the data acquisition, and also the analysis of these couplings. The solution is, the measurement is, the more easy solution is extraction of these couplings from two-dimensional spectra, and then the question is if it's better to obtain the information from the indirect dimension or the direct dimension. Then to work with the direct dimension, the advantage is that you can have high levels of digital resolution, and then the experimental time doesn't depend of the number of T1 increments. Important also is the question if we want to measure the coupling values on protonated and or non-protonated centers. If, for instance, you have a carbohydrate with all protonated carbons, probably H-squisitox is a good solution. But if you have a natural product or another molecule having protonated and non-protonated centers, carbons or nitrogens or other centers, it should be better to use HMBC or H-squin-BC experiments. Another question is if we want to measure only some coupling values, or we want to determine the complete set of coupling constants of a molecule. This is important depending on the problem we have. One question is if we want to know exactly the stereochemistry of a given center or the flexibility of a part of a molecule. Another question is if we want to set all the couplings and to put all them in a black box, like in case 3D, Roberto will talk about this, and try that in a computer-assisted way that to obtain structural information. Then it's critical the two last points. One is the accuracy and the simplicity in the extraction of small coupling values, and in particular couplings around the line width or even smaller than the line width. When we want to measure couplings smaller than 2-3 Rs, it's very important to have a robust method that we are sure that the measurement is more or less correct. And then another question that some of the methods don't discuss this is about the determination of the absolute positive negative sign of the coupling constant. In general, we can say that 1 bond and 3 bond proton-carbon coupling constants are positive, but 2 bond and 4 bond, 5 bond can have positive negative sign, and then it's very important to determine them. Then I will talk about the cell HSQ-MBC experiment. This is basically an HSQ-CX pulse scheme where the delays are optimized to a long-range value. This is a typical value for routine acquisition is optimize the delays to 8 Hz. And then the major characteristic of the selective HSQ-MBC is the central pulse in the INEP and the retro-INEP are selective pulses. And this is very important because we remove in this way important problem in long-range correlations, is the effect and the interference of the proton-proton coupling constant. That this has a tremendous effect in the signal intensity and the signal phase and also in signal modulation. I will show you some examples then. And this is a typical spectrum. The setup is very easy. You select a frequency. In this case, here are three protons overlapped. We can perform the experiment, and we obtain a set of cross peaks for the resonance excited by the selective pulse. The spectrum is clean, and then the experiment is fast because the limitation, of course, is the sample concentration, the sensitivity conditions we have, but we don't need a large number of T1 increments in T1, and then in T2 we can acquire data with a large number of time domain data points, and then the digital resolution can be very good. This is a typical spectrum, and then the main feature of the cell HSQ-MBC experiment is we obtain pure in-phase multiplets, like in proton spectrum. And this is important because in this case, this is the H8 proton in stringin. We have five cross peaks, and each of these cross peaks present a perfect pure in-phase coupling pattern where the extraction of the coupling value can be made directly. And each of these cross peaks represents the isotopomer referred in the first slide. This is the main feature that explain the simplicity and the extraction of the coupling constants with high accuracy using the cell HSQ-MBC. In cases of more complex multiplets, another approach is to measure the width of the multiplet and compare with the reference proton multiplet, and with the difference we can extract the coupling constants even in complex multiplet. That direct extraction is possible. What happens when we have complex multiplets where no is not possible the direct extraction? One approach, simple approach, is to apply the IPAP method. The IPAP method is to acquire the complementary data. This is made automatically from the Pulse program. The first data is the in-phase data, and the second data is the anti-phase data, where these two last pulses in the carbon channel are omitted. In this case, we have two spectra, the in-phase spectrum and the pure anti-phase spectrum, and then if we combine them, adding and subtracting them, we can have the spin state selection spectra. We have the alpha HSQ-MBC and the beta HSQ-MBC spectra. And then when we compare the displacement of the signals, if in this alpha beta spectra, we can obtain the coupling value. This is an example this represents this olefinic proton in stringin. In the proton spectrum is a triplet, but is a triplet with broad triplet, not well defined. This is the in-phase HSQ-MBC. This is the anti-phase. We can see that important is much better to work with in-phase multiplets that in anti-phase multiplets. The analysis, the determination of coupling constants in anti-phase multiplets must be taken care in order not to introduce an overestimation of the coupling value. That if we combine these data, we obtain two different spectra. These are overlaid, the red and the blue, and then comparing the displacement of the two cross peaks in the two spectra, we can measure the coupling constant. Then one of the drawback of the cell-HSQMBC in principle is this is a selective experiment, and then in the same way that in selective noesi or selective toxi, in principle the idea one experiment for one signal is not accomplished here. Here we can apply the method in applying, for instance, a region selective pulse exciting several protons in a specific area. In this case, we can see in a range of 1 ppm with a Reburg pulse, we can excite these 6 signals at the same time. That's these 4 of these 6 protons are not coupled, that there is no interference of proton-proton coupling constants. But in this case, we have an AB spin system, the 23 protons. And then in this case, because both protons are excited by the selective refocusing pulse, we have the modulation of the signal as a function of the proton, in this case, the geminal proton-proton coupling constant. This is translated in the analysis of the spectrum in the mix of in-phase and anti-phase contributions. But even in this case, it has been demonstrated that the EPAP method works in the same efficiency, and then we can extract equally the coupling constant value. Then what happens with the sign? A simple solution to obtain the sign of the coupling constant, because the cell-HSQMBC don't give information about the sign. A simple solution to obtain the sign is appending here, after the cell-HSQMBC experiment, to append a toxi transfer, a proton-proton toxi transfer. In this way, we have a first step is the HSQMBC experiment to transfer from the carbon to the proton of interest, and then with the toxi transfer, we transfer the information to other protons of the same speed system. In this way, because we don't apply anything during the toxi in the carbon channel, the alpha beta state of the carbon 13 is retained, and then this information will provide the information about the sign of the coupling constant. This is only one example in the machine. Is what to do is, this is the cell-HSQMBC, apply it to a single frequency, and there's the cell-HSQMBC toxi, apply it in the same frequency. And we can see that the number of the cross peaks has been increased. The nature of the in-phase, anti-phase multiplex character is completely retained. And then the only thing we must do is analyze the different cross peaks. The way to work is easy. This is the in-phase expansion. Below is the anti-phase. If we select this row, we can see the in-phase and the anti-phase. Look, here is very important that to have the criteria about the advantage to work with in-phase, the pure in-phase character. We will see the signal, the in-phase character with the note that has excellent intensity. What is in anti-phase, there is a partial signal cancellation in the multiplet, and this is an important effect in sensitivity. Then when we combine these spectra, we obtain the alpha and the beta spectra, and when we compare them, we can obtain the relative displacement of the signals. And in this case, we can see that the relative displacement of the signal, blue-red, and the other two are red-blue. That means these correlations corresponds to a two-bond correlations are negative in sign, and this is three-bond is positive. This is the reverse direction than the other two. And then this is a simple method that allows to measure first the magnitude, second the sign, and also is very important that the method allows to measure very small coupling constants, that the limit is probably the digital resolution we have in the acquisition dimension. Then many people don't like, or the non-experienced NMR users don't like the selective pulses, because you need to specify the frequency, and then you need to repeat several experiments to have the complete map. But I have commented that it's possible to apply the EPAP method when you have interference of the proton-proton coupling constant. And this is the non-selective versions of the HSQMBC experiment. This is was published, the HSQMBC PAP experiment without selective pulses is exactly the same pulse sequence, but replacing the selective pulses by using the hard pulses, the conventional pulse scheme. And using this way, using the standard sequencing, we can obtain also the coupling constant using the PAP method, is the alpha beta. We can compare slices, and we can obtain the complete set of coupling constants. And then also exist also mentioned, Thomas mentioned the PIP HSQMBC, that it's possible to obtain the pure in-phase HSQMBC spectrum, to obtain completely in-phase multiplets that is more easy to analyze. Then to finish, two questions, two articles that we have published this year is one of the problems of the HMBC. One of the problems of the HSQMBC is what happens with proton-proton modulation. And only to exactly to see which is the real drawback to apply broadband HMBC or broadband HSQMBC experiments can be observed in these simulations. Here below, we have the profile of a signal of a given spin system using the cell HSQMBC, where we don't have interference of the proton-proton coupling modulation, that the signal presents perfect pure in phase, and the signal intensity follow a sine modulation. And this is the same spin system exactly under the same conditions, but having the modulation of all proton-proton coupling constants. We see the two effects. First, we have an important decrease in sensitivity, and then sometimes we have partial or full cancellation of the complete multiplet, and this is the reason that sometimes in HMBC or HSQMBC some expected cross peaks are missing. And then the other question is, you can see the mixed phase of the multiplets. We have compared the selective version with the broadband version in an experiment optimized to 3 Hz. This is the long range HSQMBC and the selective version. And then when we compare the both spectra acquired exactly under the same conditions, only changing the selective pulse with the hard pulse, we can see the difference and the better performance of the long range cell HSQMBC experiment. Better sensitivity and full pure in phase character for all cross peaks. And then to finish, in another article we published this year in ChemPhysChem, we have shown that it's possible using this long-range cell HSQMBC experiment, using this is the in-phase multiplets, and this is the IPAP multiplets. We can measure couplings in the range from 11, 12 Hertz. In this case, are proton-nitrogen, proton-carbon coupling constants, or couplings smaller than 1 or 2 Hertz. This is all from my part, and let's say to Roberto now.
Thank you, Thomas, for the invitation. What I'm going to I am here kind of outsider because I'm not an expert on past programs and calculations and J analysis, but I had to say that I've been using J couplings as an structural elucidation for many years, especially in my work with natural products. That was the beginning and how I started in science. I'm gonna just share with you a work that we did that it was very nice, and I would say that also there was a lot of serendipity here, what we found, and is using this beautiful HSQMBC experiment and then use it for a structure selection. So what we did is in the past, we've been working on anisotropic NMR. So after all our work with anisotropic NMR, that this is most of the work that we've been doing in our group, we developed this, it's a kind of extension of the case that use all the through bond correlations to get a configuration, and there is some application with some NOE. So extending this from constitution to configuration and conformation. And this article that we published a few years ago, 2018, the idea is we call it computer-assisted 3D structure elucidation, which is just an extension of case for 3D with natural products. So, and you can see here is a kind of Swiss Army knife in which you can combine all the different NMR parameters. The idea behind this method was that if you have a set of experiments and you know, you need the molecular formula, a proton, carbon, and true bond correlation experiment, you use your preferred computer case program, computer-assisted structure elucidation, that I will say that the best two in the market are ACD Labs and Bruker CMCSE. And then what you do is you generate your structure, that is your constitution, and then you use your preferred software to generate the configurations. And then you generate 2 to the n-1 when n is the number of chiral carbons. And then if your molecule is flexible, you use your preferred software to generate the conformational space to get 2 to the n conformational sets. Then you perform analysis. You can use, normally you can use molecular mechanics, DFT, and you could use GAO calculations, and then you can calculate NMR parameters. You can calculate DFT geometries, proton carbon chemical shift, the CSA tensor for chemical shift and for RCSAs. And also you can calculate your J couplings as already was described by Alexie. And then what you do is you compare your experimental parameters with your calculated parameters, and then you perform a fitting. And then you, for example, this is just a fitting of carbon NMR only to the 32 isomers of artemisinin. And you can see that the correct structure is selected by using a kind of a score that in this case called the AIC. So this case 3D, that is just a program to perform selection of configuration and conformation, is just a multiple NMR parameter fitting protocol to determine configuration and conformation. And you can combine RDCs, RCSAs, chemical shift, scalar couplings, and NOE-derived distances. Of course, that when it comes to scoring, so the idea is that what you do is you calculate your chi-square, and then you sum the chi-square of your J's, your distances, your chemical shift, your RDCs. And then what you need to do is, the only way is that since you are comparing different type of parameters, for example, Hertz, Armstrongs, ppms, and Hertz, so you need to scale them and divide them by the error. So what you do is you calculate the error, and then what you need to do is, as long as you really know the uncertainties, you can perform this combined analysis. You can read that in the article. Then we use a model selection. If you have a conformational space, we use this archaic information criterion that I'm not gonna talk much about. This is in the article, and this is to prevent overfitting. So we published recently this article in which we use the long range. We use 2 and 3 bonds, coupling constants, proton carbon, for computer-assisted structure elucidation. This was done with my postdoc, Martin Cus, with Armando Navarro Vasquez from Brazil, and Clemens Anklin from Bruker Corporation. So what is very important is that, as already Alexie mentioned, the importance, for example, of the 1 bond. So all J coupling constants are highly sensitive to the electronic structure around and between the coupling nuclei. Albeit without the simple 2-way interpretation of the 3 bond. Yeah, the 3 bond is easy, you will see, it's easy to interpret because there are equations to do it semi-empirically. With access to quantum chemical calculation, and now, especially computational cheap DFT, you know, we can calculate this coupling constant with enough accuracy that is already mentioned in the other talk. And you can see here some articles. All available nJxY coupling constant can be utilized for structure elucidation as long as they are experimentally accessible. That's the other problem. Theo was teaching us how to extract them, you know, with accuracy. And, you know, they are becoming increasingly accessible, as recently covered in an excellent review article here. That's the article by Theo. So Theo already showed you how to really do this, you know, and how to measure them. So I had to confess that I was part of this group in the community as a natural product chemistry, in which we really believe that only the 3-bond coupling constant through this Carpenter equation was the only probably best information to get angular information. But I think that I was wrong, a part of the many people, that they don't know exactly that every J has a value and has a structural value. But when it comes to the 2 bonds proton-carbon coupling, which is very valuable, already in 1969, I found this paper. You know, they were, you know, showing the coupling constant between carbon and proton through 2 bonds, you know, and they were showing just the importance. Then you can see this nice review in year 2000 by Contreras and Peralta. And then they mentioned that the angular dependence of the 2J coupling that have interesting potential for stereochemical analysis. We're talking about 2000. 10 years later, 2009, again, use of 1 or 2 bond coupling constants for the study of conformation and configuration following this trend. These were described substantially increase in the 2J potential as proof to analyze stereochemical aspects in organic. You know, and it's funny because we got that article in 2000. We had that article in 2009. We are in 2020, and we don't see, you know, the community really exploiting the power of this. So as I told you, there are methods that exist to measure them. They already told you. And then we had these beautiful pure in-phase heteronuclear NMR experiments, an article, you know, here. And in the value of the 2J coupling constants, they say all coupling constant depends on the electronical structure. DFT provides 2Js and 3Js at sufficient accuracy. And I said again, there are also NMR experiments to measure them. So what we did is that you just took a string, we use the IPAP, you know, pure in phase, HSQMBC, optimized for 8 Hertz. And as Theo mentioned, I am sorry to hear that there are some issues with the broadband, but in one shot, we measure 32 2Js and 47 3JCH unsigned, you know, and then we calculated. We didn't test all the possible options, but Armando calculated the coupling constant using the PBE0 functional, and then the basis says 631 G double star, and we calculated by DFT. And then we compare them using score. So here you can see just a picture of the experiment that we measured, and we just collected one experiment. And what is the scoring method? Well, the scoring method here, we use this one, you know, that I already mentioned to you here. But what we did is, since we are using only J's, okay, we use the chi-square, and in which we just score only the J values. But since the molecule, since strychnine is rigid, the AIC is equal to the chi-square. So we didn't use really, we use AIC, but the AIC, in fact, here in this paper is just the chi-square. Using semi-empirical methods to calculate J couplings, we have this Bifulco equation. Bifulco proposed a Karplus type equation for the 3 bonds. And what we did is we just used the 32 J couplings. Oh, sorry, this is wrong. We used the 3 bond. And then when we compare our 3 bond couplings against the Bifulco equation, also keep in mind that the Bifulco equation only works with proton, carbon, carbon, carbon fragments. So if you have a nitrogen there, you cannot use it. If you have an oxygen, you cannot use it because it's semi-empirical. But even using this, the correct structure is selected. But when we use DFT calculated J couplings, and then we use them all together, the 2 bonds and the 3 bonds, we select the correct structure again. If, in this case, if we use the 2 bonds only, we got the surprise that using only the 2 bonds, we see also the selection, which is impressive because if you ask most of the community, what would you use, 3 bonds or 2 bonds? Everybody has this concept that is easy, that is only the 3 bonds give you angular information. But there is a dependence of the angular dependence. The problem here is that it's very difficult to get a universal, semi-empirical equation, but to parameterize this for the 2 bonds. And the only way to get this information is performing DFT calculations. So here, what you can see is that the 2 bonds here and the 3 bonds, and all of them select. So we were really impressed and combining them. And I would tell you that it was a kind of serendipity because we decided to measure getting these calculations. And the reason why we got this is because we did DFT calculations. And it was very easy to get a DFT calculation. It was very easy to measure the coupling constants. So what I can say is that both have similar power. They are suitable for 3D structure. They are easy to measure. And of course, they require DFT calculation if you want to use them. I want to really thank Claudio Tormena because when we found this, there were some discussions with him because he already published that article before. And then, well, yeah, we have very good discussions with him and we searched the literature to see what it was done and we found that not much was done in terms of doing a structure selection. So with this, we just thanks for your attention. And now I think that the discussion should be open.
Fantastic. Thanks, everybody. So we'd be more than happy to answer any questions if folks still have some ongoing thoughts or comments that they'd like to share.
Theo, I have a question. Let me ask. What do you think is the lower limit of detection of the J couplings of the 2D NMR spectroscopy that you can reach, and how you can estimate the accuracy? Can you give some thoughts about that?
In the case of the nJCH QMBC, if you use a large number of data points in the acquisition, you can achieve a digital resolution of 0.3, 0.4 just before processing. And then, well, this is the limits of digital resolution. Using the nJCH QMBC and the acquisition dimension. Then in other methods, this probably is the maximum you can achieve. That it's true that in the original articles 30 years ago, performing fitting, I don't know, I have no many experience on this, on the fitting procedure and the simulation procedure. But digital resolution and line width are the main limitations to obtain with more accuracy the coupling constants. And then the major problem, I think, I don't know in the future, is when you have couplings with a magnitude of 1 or 2 hertz, the question is to know if they are positive or negative. It's not the same to have +1 or -1. There are a lot of error if you don't determine the sign. And then this is the advantage to select one experiment that determine the sign, because the calculations give the sign, and then the correlation could be better. I don't know if in the future there can be make some things about this, but this is important thing.
There is a question in the chat that probably this question maybe is for Alexie, because he says, how does one practically get started looking into DFT? And then the same person said, for example, is there any website you deposit data into? There is a software, documentation, learning curve, etc.
Okay, so how to start with the DFT? Well, of course, there are plenty of information, and on the internet, there are some courses. I mean, you need to understand a little bit of basics, but practically, since we're talking about the workshop, you need an access to the software program that can calculate. And then I'm personally, I like Gaussian. The Gaussian is a well-established platform with probably one of the best, and not only for the NMR calculations. That program can be installed on any computer, even on laptop. Better to have it's on a workstation or is on a cluster, as we have here. It gives you capability. But I have to tell that my first 5 years of using the Gaussian, I was running that software on a regular laptop and on a Windows computer. So it has it can be run on Linux, is better, of course, but on a Windows you can run, and a lot of information and a lot of interesting structure analysis has been done on a regular, simple, very slow and old computer with 4 cores. So this is how to start. Once you have the software, you will learn very quickly with the available manuals that there are just a few keywords that you can have to specify when you run the calculation. So before the calculation of the NMR parameters, you have to do the geometry optimization, and basically it's one line with the 2, 3, 4, 5 keywords, which is a well described on a Gaussian website, and there are plenty information available in the out there how to compile this small file, and we actually, if you will look into our publications, we quite often putting that input file for the Gaussian into our supporting information file. So you can follow that, but I can tell you that there is plenty of information out there, and so having this program, having this the molecule, you have to sort of prepare the coordinates for that molecule. For that reason, you can use any molecular modeling software, do the quick optimization using force field, take these coordinates as an input file for the Gaussian, and then with the one keyword putting there in the calculation for the Gaussian, you will get the full table of all couplings if you want, and then you can play around with that. So that's.
I use a software that I pay for the license, that is the Schrödinger. That I use the Schrödinger leak prep and a macro model. But for example, Avogadro is a free software, and you can generate a mol file with even ChemDraw, then read it with Avogadro, and Avogadro can create an input file for Gaussian, for Orca, and for many software. So you are short on money. I think that's also a good solution. The problem is that an academic license for Schrödinger is about $1,500 a year. So yeah, that's about your budget. There is someone here. Let me see in the that want to ask a question. Can they unmute themselves? Siddhartha Sarma. Siddhartha, you want to ask a question?
Yeah, good evening, and thank you very much for this discussion group. I have a question. I mean, this can be answered by any of you all on the panel. What is the size limit of molecules for which these and I call them very long-range couplings that can be measured? I know, of course, it will depend on the line widths at the end of the, when one really takes this into consideration. But has anybody explored the size limit, like small natural peptides? Has anybody looked at these?
Well,
I mean,
I think the limit is not only the molecular size, is the T2 relaxation
yes.
times you have.
Yeah.
And then not only is the size, also if you have dynamical processes, for instance, one of the limitations of the experiment I have presented is this is a refocus Hitachi's QueenBC experiment. And then if you want to try the experiment using long delays, obviously for molecules, medium-sized molecules having short T2 times, probably you will lose a lot of signal. Then this is the reason, because doesn't exist a method, a general method that solve all the problems. And probably in this case, when you have large biomolecules, but the problem is not large, is you have a short T2 times, you need to select an experiment the shortest as possible in time. And then other options would be required.
I mean, for instance, has anybody tried it with, let's say, peptides of, about 8 residue, 9 residue peptides? I mean, have you tried it? I just want your experience on this. I mean,
I personally measured the same experiment. It's now published on Taxol molecular weight 850. So
okay.
and I've seen beautiful data. So, but it's, as Theo said, it's depending on the T2.
T2, yeah. Taxol is another nice rigid molecule. It's it's very nice and rigid.
But cyclosporine, for instance, has 10 amino acids, I think.
Yes.
And you have nice spectra. 10 amino acids is a small molecule,
Oh,
then, no problem for this size. I think if there is no other problem, Okay.
So cyclosporin, oxytocin, those kind of molecules will give you good data on these long-range couplings.
I think so.
Is that from your experience? I mean, that's all. That's nice to know. Thank you very much.
Yep.
I really appreciate this.
There is a question for me from Davi Sinab asking about, you talk about geminal CH-J couplings. So do you know examples of geminal proton-proton couplings being exploited? Well, there are not examples, but they are also sensitive. Every J coupling is sensitive to configuration. That's the amazing part of this. And I'm pretty sure that some of them are more accurate if you minimize the geometry as with the DFT, because DFT will give you the correct bond length, as also explained by Alexie. And this is a question for Alexie here. What is the limitation of DFT calculations? Would you be accurate for molecule with molecular weight 1,000 Daltons?
Yeah, well, probably the largest molecule that they have been looking at, it's around 500. 1,000 is a little bit too much, but there are ways of reducing the costs if you do analysis by fragment. And I think David Case in Rutgers is doing that pretty successfully for the small proteins. So he would be sort of fragmenting the molecule and then calculating locally. And then it's because so if you know the environment of the large molecule, the fragment of the environment, you can sort of separate that and do local analysis. So in that case, there is no limit. But if you want to calculate the whole thing, then it's probably the more feasible size is around 200 to 300, because it will give you a reasonable time of the calculations, which would be measured by hours, not by days or weeks. And of course, it's depending on what kind of coupling you want to calculate. There are, in Gaussian in particular, you can specify, I want to calculate only this coupling and only that parameter. So, and that can reduce the time of the calculation significantly. So there are a way to overcome that if you will be focusing on the small amounts of the couplings or sort of local stereochemistry problem. So I hope I answered the question.
Alexie, I have a question for you.
Okay.
What would be a decent, I would say cheap in terms of time, to get a decent geometry by DFT? You know, a combination functional basis set that you say, okay, I have a laptop, okay, like with an i7 processor and one core, for example. Yeah, it's very limiting, but what is the threshold, the minimum to get a decent geometry?
Well, honestly, I mean, it's like a full disclosure. I mean, we have been using for years molecular mechanics, which is also a very powerful tool. So I'm not always going directly to DFT because it's time consuming, and particularly for the flexible molecules, you cannot calculate everything with the DFT if you have 1,000 conformations. So you need to do the pre-screening whatever your molecule is, and you may have a very small molecule of the weight of 150, but it can have 1,000 conformation, and you'll never be able to finish the work even if you have a supercomputer. So that's not the point. So if you want to know the geometry, I would start I would start molecular mechanics, and maybe the best molecular mechanics which we have. And
well,
you mentioned Schrödinger. It's a good starting point using the Schrödinger, for instance.
I would say I've been very proficient using molecular mechanics. I use it a lot every day. I use this MMFFS, okay, and in macromod. It's give you very pretty decent. We already did some work with calculation of chemical shape, but your paper is an eye-opener when it comes to bond length. So I'm not gonna get the accurate bond length with molecular mechanics. Then I need to jump into DFT. So, but I need a minimum, you know, like recommendation on what is gonna give me the real bond length that I need, because the one bond depends on the bond length.
Well, so you mentioned the geometry and the bond distance. Well, it's a difficult to answer because the difference that we are getting is 1,000th of the angstrom. There is no way that we could experimentally confirm that this geometry is right or wrong. This is just the better geometry. Better, I'm in quote, is actually is better, which fits to DFT method. You have to remember that the DFT is also a very empirical method. So there are a lot of parameters within DFT which has been experimental scaled using the experimental data, and that scaling was not necessarily fits NMR purposes. And that's why choosing the right geometry, it happens that we're using for the one bond coupling in particular, that is extremely important parameter.
Yeah.
It will be not as important for 2, 3, and 4 bond correlations, because you have a much bigger distribution of the angles in between and accuracy of the angles. Now you have to think about that. Of course, there is a vibrational corrections, which is has to be taken into account as well. So, and a solvent effect and others. So you have so much what's going on for the molecule in a way. So I would be kind of cautious to say that the perfect geometry is needed for those type of calculations. It is important for the one bond, but as far as for the N bonds, I don't think this is so critical.
Well, in our paper with the M bonds, we did it with molecular mechanics and then DFT calculated. But I coming back to your paper, your paper is critical. You know, if you don't have the you don't have the correct bond length for the one bond, forget it. I was also after reading your paper, I compared DFT calculated distance with MMF distance, and you know the MMF distance are pretty constant because it's just
it's one parameter.
It's one parameter. Well, there is a question here. They said, Roberto, you mentioned that heteronuclear like nitrogen are problem when performing DFT calculation. No, I didn't say that. What I said is that if you want to use the bifurco semi-empirical equation, it doesn't work when you have nitrogen or oxygens. But then you are asking about probably performing this calculation for nitrogen, and what about sulfur? This is a question for you, Alexie, again.
Well, what's the question? I mean, the question
is say heteronuclear like nitrogen are a problem when performing DFT calculation. When I didn't say that, and then say, what about sulfur?
Okay, but talking about the nitrogen, we have studied that, and proton nitrogen in heterocycles has been predicted pretty well. I didn't have any problem with the B3 lip and a triple Z basis set, which is a 6-311 plus GDDP. Usually that we use, and that's our favorite, and with the mix setting for the basis set. We haven't published that because a lot of proton nitrogen correlations that we saw is actually for the compounds that is proprietary, so for that particular reason I cannot sort of disclose that, but I can tell this is for years we have a very successful to predict HMBC, proton nitrogen, and BC cross peaks based on the DFT calculations of those. There is one little glitch of predicting those couplings. One have to remember that the Gaussian would calculate the coupling for proton and nitrogen 14, and it have to be all calculated couplings for the nitrogen has to be, because we are observing in N15 space, so not N14, and there is a gyromagnetic ratio of the two would be affecting the calculated coupling. So each and every coupling that you're calculating with the Gaussian has to be multiplied by the coefficient, which is a ratio of the gyromagnetic ratio of the two nuclei. And it's, that could be a little bit confusing because once you calculate it, you see that they're small, but then you have to remember that the output is not exactly what you're looking for. So multiply by minus 1.4 roughly. And then we have a very good experience with that. As far as the sulfur, we are not calculating coupling with the sulfur because we're not observing those. And as a heteroatom present in the molecule, it might deviate sort of the couplings. Sulfate, sulfoamide, we have been using those. We haven't seen any big problem to predict the CH or CN or HH coupling in the presence of the sulfur. So that's maybe unknown to me. There are some molecules which have that problem. What we have problem with fluorine, that's the nuclear which is disrupting for the DFT analysis. It is the couplings with the fluorine is notoriously difficult to predict. There is still ongoing work, and we are the part of that work as well. And so we soon we're going to publish something about that. But we're not the only one who is checking. So that's my short answer.
So I think one other question that someone had was
Armando. Yeah. Sorry.
Oh, Armando Ariza. Oh, yeah. I think.
Yeah, Armando Semi. I would like to two things. Gary comments something about the importance of screening in our lives, and that's a good thing because. There are many articles using the screening, and at least it can be used for comparing experimental data. And then I think it's important that to use different labs with different methodologies, the same molecule, because we have not only coupling constants in general in NMR data is important. And related to the question of Armando, it's about the G upscale experiments. For instance, the JHMBC or the selective version. This is the EXCITE experiment. The problem of these experiments is that you measure the coupling constants from the indirect dimension. And then a strong requirement, if you want to measure coupling constants from the indirect dimension of a two-dimensional spectra, is you need to have high levels of digital resolution. And even if you use GS scaling methods, you need a large number of T1 increments. And also another problem is the scaling of the error. And sometimes it's difficult to make accurate measurements when the coupling is below 2-3 Rs, even if you use upscaling methods. And in principle, in general, these methods are more time consuming than the equivalent of detecting the same signal in the if2 dimension. For instance, the Selachis-Quimby experiment is the equivalent of the EXCITE experiment that proposed Krishnamurthy, I don't know, 25 years ago.
Yeah,
It's
96.
equivalent, yeah, 96, yeah. And it's much better to measure the coupling from the F2 than the F1. Experimental time is shorter and the digital resolution is better.
I wanna mention, because about the comment by Gary about stringing, I want to tell you guys that my research says that Gary has the gold medal of papers published with strychnine, 47. He's leading the board. So if you want to catch up with him, yeah, you had a lot of
Hurry up.
Yeah. But there is one with 46 or something in SciFinder. I don't know who is there, but Gary, you have to hurry up because someone will, catch up with you. I can't catch up. I don't have more than 10 with strychnine. Okay, I don't know. There are more questions here, so this is going very nice.
Yes, if there are any more other questions. Otherwise, I'd like to thank our panel for very interesting and turn it over to John for final words.
You guys keep raising the bar with these meetings. Fantastic discussion today, and many thanks to Thomas and Teo, Alexie and Roberto. Great meeting today, and really looking forward to the next one. Dan, could you remind us once again what we've got coming up?
Hey, hold on, sorry, 1 second. There is just one more question here. Can we answer the question?
Sure, yeah.
Certainly.
Please.
Yeah, I don't know for whom it is. How about Ray Freeman and bromopropionic acid? It's about the papers, probably. I think that's my understanding. Okay, I don't know how many papers on bromopropionic acid Ray Freeman has. Okay, that's Dimitri. Okay, I think that we can close this now.
Okay, so the next meeting is about covariance processing, and the schedule is not quite set. It's going to be the week just prior to Thanksgiving. And I think the panel leader is David Schneider.
And Dan, I think we also have various things planned. Gee, are we out towards sort of February? At this point?
Yeah, I think Krish has a number of them in backlog. We're trying to do 1 or 2 a month, and yes, he has. I was just looking to see what his list is. Yes, he has a number of them.
We must be doing something right.
Sounds like it, yes.
Thank you, everyone, for attending today.
Thank you.
Well, thank you.
Thank you.
Thank you. Goodbye.
Bye.